So, say we want to draw the PV diagram first. So, in terms of pressure and volume, we're going to have to look at what happens to the pressure and the volume in each of the cases for the piston cylinder arrangement. So first of all, what's going on? This is your piston, and this is your cylinder. You have an intake valve and an exhaust valve. Top dead center is at the top of the cylinder, where you have minimum volume. So when your piston is at the top of the cylinder, you have minimum volume. And when you're at bottom dead center, at the bottom of the cylinder, you have maximum volume. So, what's going on first of all? Through the intake valve, you're going to have air coming in to the cylinder. This air is coming in at atmospheric pressure, P0. So pressure is constant. We said we're looking at P and V for PV diagram. So what about the volume? Well, in order to make space for the air to come in to the piston, you have to pull down the piston in the cylinder from top dead center to bottom dead center. So you have space. So we said pressure is constant, atmospheric pressure, and volume is increasing. So constant pressure means a horizontal line. And to make the pressure constant, it's going to be the same point. So from 0 to 1, that's what we said, because we're moving from top dead center to bottom dead center. Look here. Top dead center, bottom dead center. The piston is moving from top dead center to bottom dead center. So through the intake valve, you have air coming in and filling up the cylinder. Okay, that's for 0 to 1. Next up, from 0 to 2. This is this one. Compression stroke. So, in terms of pressure and volume, your piston is going to be moving up the cylinder from bottom dead center to top dead center because we have compression. So your volume changes. Let's write this for gradient. What happens to the pressure? As we're compressing, there's going to be a slight increase in pressure as well. So volume, we said, from bottom dead center to top dead center, since we are compressing. From bottom dead center to top dead center, and we said we're going to see a small change in pressure. So, this way. Next up, from 2 to 3. From 2 to 3, we have spark ignition. So, what happens to P and V? V depends on the piston cylinder. Our piston cylinder is not going to move anywhere. It's going to stay there. And our intake valve and exhaust valve, imagine they're closed, so just neglect them for now. This means constant volume, since our piston cylinder just stays at the top, while we have spark ignition. Spark ignition means that the temperature of the air or the fluid or whatever you have going on is going to increase. You're going to be burning fuel. So an increase in temperature means an increase in pressure. So heat addition, increase in temperature, and by increasing temperature, within a constant volume, you have an increase in pressure. So constant volume, because the piston is just staying at the top, V is constant, and pressure increases because the temperature increases because of the spark ignition. So we said constant volume and pressure increase. You can see we have constant volume at the top dead center, here, and pressure increase. Okay, next up, from 3 to 4, in terms of P and V. V is determined by the piston cylinder. What happens to it? We said it was at the top during spark ignition. so it was here. It gets pulled down because we have isentropic expansion. And expansion means an increase in volume. We are increasing volume, but at the same time, by increasing the volume, the pressure is going to drop because you have more volume. So more space, so less pressure, so less crowded, if you want to think of it like a bus or train or something that's less crowded because it's got more space. Anyway, so we said isentropic expansion from 3 to 4, which means from the top dead center moving to the bottom dead center. And you also see the change in pressure. Next up, finally, from 4 to 1. Through the intake valve, you have air-fuel mixture in. Volume is going to be constant because what did I say? From 4 to 1. The piston is just going to be staying at the bottom dead center. Ignore this. Okay, so now for the TS diagram. Oh, one more thing. You see these two lines between 2 and 3 and 4 and 1. You know they're both vertical, but how do you know which one's shorter, which one's longer? You know that from 2 to 3, we are adding in heat from 2 to 3. Heat addition because of the spark ignition. So this is Q in. So by the time you get here, Q out. Which one's bigger, which one's smaller? Well, you know that the net heat energy, the net heat is the heat in minus the heat out. Because you can't really produce more heat without wasting work. So yeah, because of the net heat, the Q net line has to be greater than the Q out line. Okay, and finally, for TS diagram, what's going on? From 1 to 2, isentropic compression. Isentropic means constant entropy. So the S at 1 is the same as the S at 2. This is S, so it's going to have to be a vertical line if S1 and S2 are constant. Same goes for 3 to 4, isentropic expansion. So entropy is the same, so vertical line. And then we're going to add the numbers later. These two lines. Now the other two. Between 2 and 3, we have constant volume heat addition. Heat addition. This means that your line from 2 to 3 has to increase to make up for this change in pressure. Increase. If it was decreasing, it would be going down. And between 1 and 4, or basically 4 and 1, constant volume heat rejection. If you're rejecting heat, you can see this would be the change in temperature by rejecting heat. So it's going down. So that's how you know at what kind of angle or height to place these two lines. Yeah. And finally, compression ratio. This is the maximum volume over the minimum volume. In this case, our maximum volume occurs at 0.1 and our minimum volume at 0.2. Or you could also write volume at 4 over volume at 3, because you see bottom dead center over top dead center, same thing. And you can also write it in terms of smaller v's, so per unit mass, v1 over v2. That's compression ratio. Now for isentropic efficiencies for Otto cycle. If you have air standard assumptions, you can use this formula, which eventually is going to simplify to this. But that is only for cold air standard assumptions. If not, just use the regular one.